So there have been some questions about how to do a couple of the problems on the sample exam. I thought I would record a quick video to help you through solving these two examples. So the first one, the question was for the following peptide, what is the net charge at pH 5? So whenever you do a problem like this, the best thing to do is start off by basically putting the amine group and the free amine and the free carboxylic acid that's present. So basically out here on the alanine, you're going to have a free amine group that's going to, in general, have a positive charge. But we'll double check that later when we look at the actual pH. And then on this methionine, we will have a COO minus, a carboxylic acid that is deprotonated. The next thing to do is to go through and just get rid of all the amino acids, at least the R groups that are not ionizable. So we don't worry about alanine, we don't worry about valine, and we're not going to worry about the R group on methionine. But we obviously do have to worry about the amine group and the carboxylic acid at the end. The next thing we do is go through with the others and we assign their charges, and notice that the amino acids that are left are all ionizable amino acids. So histidine has the imidazole ring in its R group. The imidazole ring, in this case, histidine has a pKa of about 6. So we are below the pKa. The pH of 5 is less than the pKa of 6. So we expect histidine to be protonated. And when histidine is protonated, it has a positive charge. So from histidine, we get a +1 charge. Arginine, pK for arginine is about 12.5. At a pH of 5, we expect arginine to likewise be protonated and therefore bear a positive charge. Aspartic acid has a pK of about 3.8. In this case, we are above the pKa, and aspartic acid containing a carboxylic acid. A carboxylic acid, when it's above its pKa, it's going to be deprotonated, and thus it's going to have a negative charge. Cysteine, although it is an ionizable amino acid, the pKa occurs here at 8.3. Below 8.3, it's protonated, and when cysteine is protonated, it is neutral. So I'm going to put an N for cysteine to indicate that it's neutral. Cysteine does above its pKa. If we were dealing with a much higher pH, something above 8.3, cysteine would be deprotonated and thus have a negative charge. But in this case, because we are below the pKa, cysteine will be neutral. Will be protonated and therefore be neutral. The last group we have to consider is lysine. Lysine has an amine in its R group, and the amine group in this case, the pKa is about 10.5. So we are below the pKa for lysine, and thus we expect a positive charge. Let's check the amine group in the carboxylic acid at the N-terminus and C-terminus of the protein. The amine group here, generally the pKa's for these amine groups somewhere between 9 and 10. So at pH of 5, we are distinctly below that, so we expect a positive charge from this amine group. For this carboxylic acid over here at the end, the pK in this case is about 2. We are substantially above that, so we expect it to be deprotonated, and carboxylic acids bear a negative charge above their pKa. So if we go through and count up the total positive charge, we see that there are 4 positive charges and there are 2 negative charges. Combine those together, we get an overall of a +2 charge for this peptide. So any problem like this that you have to do, basically you simply go through and, as I did, cancel out the amino acids that don't have ionizable R groups, put in the amine terminus and the carboxy terminus, the amine group and the carboxylic acid that occur at those places, and then go through and assign charges to each of the individual amino acids that are ionizable. And then when you're all done, just add up the charges. Remember that each amino acid is independent of the amino acids next to it. So you just treat each of those amino acids independently, and you shouldn't have a problem. All right, the next question on the sample exam was asking for the isoelectric point, and basically you were given several options, so you don't actually really need to go through a full calculation of this. You just have to kind of get in the general ballpark to get it right. Now, what you would do in this case is, just like with the previous, put your free amine here on the leucine, and then over here on the serine, put your free carboxylate. And then the amino acids that we're going to consider in terms of those that are ionizable would be aspartic acid, lysine, and arginine. These are all going to have ionizable R groups. And what I like to do is just go through and put the charge at pH 7 just to kind of give us an idea of what we're looking at so we can start canceling some of these charges. So aspartic acid at pH 7 is going to be negatively charged, whereas both lysine and arginine are both going to be positively charged. So now we're going to start actually canceling out the charges that are or cancel out whatever charges we can. So we're going to start off with the two extremes. So the extreme negative charge, well, our two negative charges are aspartic acid, pK of about 3.8, and the carboxylate of the serine, which is down around 2. So this is the serine carboxyl is going to be the extreme for the negative charge. The extreme for the positive charge, well, arginine has the highest pK at about 12.5. So we're going to cancel out the arginine with the serine carboxyl because those are the extreme negative and the extreme positive. So now we're left with a positive charge from lysine, positive charge from the amine group on leucine, and a negative charge on the aspartic acid. So we've got an imbalance of charges. So what we need to do is find the point at which the amine group from leucine and the R group of lysine contribute a +1 charge to counteract the negative charge from aspartic acid. This is just like the problem that we did in class where we were calculating the PI for an amino acid like aspartic acid or lysine. Basically, we're looking for that point at which the two positive charges give a total of a 1 positive charge to counteract the negative charge from the aspartic acid. So the isoelectric point from this is going to be basically the point between the pKs for the amine group of leucine and the pK for lysine. So here we have a pK of about 9.6. Here we have a pK of about 10.5. And we want the point at which the leucine amine group is mostly in a deprotonated state, whereas the lysine R group is mostly in a protonated state. Because what that means is that at that pH, we're going to see that leucine contributes a little bit of positive charge, lysine will contribute a lot, but both together will add up to a +1 charge. So in this case, the PI is going to equal 9.6 plus 10.5 divided by 2, which there's a choice given of 10.1, so that would be the correct isoelectric point for this peptide.